welcome to Talk Tensors.
Glad to be here for this one.
Yeah, today we are embarking on a deep dive that, well, it looks at the very foundation of how we put artificial intelligence into the palm of your hand.
Or literally into the sky.
Exactly. We are examining a classic, really seminal computer science paper that fundamentally revolutionized how we think about bringing advanced AI to resource-constrained devices.
It's a hugely important piece of work.
The paper is titled ShuffleNet, an extremely efficient convolutional neural network for mobile devices.
Published right around 2017.
Right. And if you've ever wondered how your phone or a tiny microdrone or even your robotic vacuum can run complex image recognition without just melting its battery.
Or requiring you to wear a supercomputer in a backpack.
Yeah, exactly. If you've wondered about that, today's deep dive is absolutely for you. We are going to explore the architecture, the math workarounds, and the really brilliant hacks that made edge AI a reality.
To truly appreciate what this paper achieved, we have to kind of transport ourselves back to the state of computer vision around the time it was published.
The dark ages of 2017.
Right. The prevailing philosophy in the field back then was, quite simply, bigger is better.
Oh, absolutely.
Researchers were just primarily focused on dominating the ImageNet leaderboards.
And ImageNet, just for those catching up, is that massive visual database designed for object recognition research.
Millions of hand-annotated images.
Yeah.
And the way you won on ImageNet back then was by building increasingly deeper and larger convolutional neural networks.
CNNs.
Right, CNNs. We're talking about architectures like VGG and ResNet.
Huge models.
Incredible feats of engineering in their own right, but monstrously large. They had hundreds of layers, thousands of feature channels.
And the compute budget for those was just...
measured in the billions of floating point operations.
Yeah.
DFLOPs.
Yeah.
VDG-16 required over 15 billion FLOPs for a single pass of a single image.
Let's contextualize what 15 billion operations actually means in the physical world, because it sounds abstract.
Sure.
If you are running that model in a massive server farm with dedicated industrial cooling...
and a direct connection to a power grid.
Right. Then 15 billion FLOPs is just a fraction of a second of compute time. It's nothing.
But if you try to put that same computational load onto a smartphone from 2017...
you are going to run into absolute physical walls.
Very hard walls.
You have a lithium-ion battery that holds a very finite amount of energy. You have a processor crammed into a millimeter-thick chassis.
With zero active cooling. No fans.
Exactly. So if you ask a mobile chip to crunch 15 billion math problems just to recognize a coffee cup in a photo, your phone's thermal envelope is breached almost immediately.
The processor throttles its speed to prevent the silicon from literally melting.
The app freezes.
And you just watch the battery percentage visibly plummet.
So the entire industry was caught up in this arms race for maximum accuracy, throwing these massive compute budgets at the problem.
But the authors of the ShuffleNet paper looked at the exact opposite extreme.
Which is what makes it so fascinating.
They weren't asking how to squeeze out an extra 0.1% of accuracy with an infinite power budget. They were asking a much more difficult engineering question.
Which was?
How do we get the best possible accuracy with an incredibly strict budget of just 10 to 150 megaflops?
Megaflops, not gigaflops.
Right. We are talking about 100th or even 1,000th of the compute power of those massive server-side models.
They were looking at common mobile platforms, drones, robots, smartphones.
Where you don't just worry about processor speed, you worry about those severe thermal limits and battery constraints you just mentioned.
But there were other approaches floating around at the time trying to address this mobile gap, weren't there? People were trying to shrink the big models down through post-processing tricks.
They were. Network pruning was popular.
Right.
Which is essentially training a massive network and then trying to snip away the artificial neurons that didn't seem to be doing much.
Just trimming the fat.
Exactly. There was also weight quantization.
Taking the high-precision 32-bit floating point, numbers the parameters, and crushing them down.
Crushing them to 8-bit integers. It makes the math simpler and faster.
But this paper took a far more foundational approach.
They didn't want to just compress a heavy, inherently inefficient architecture. They aimed to design a highly efficient basic architecture from the ground up.
specifically tailored for extreme computational constraints.
Because they recognize that the fundamental building blocks making giant networks successful were actually structurally flawed when you scale them down to tiny dimensions.
Okay, let's unpack this. The paper introduces a thesis to solve this that revolves around two highly novel operations.
Pointwise group convolution
And the channel shuffle.
Together, these drastically reduce computational cost,
Which allows the network to actually be built wider, meaning more feature channels.
while maintaining high accuracy on mobile platforms.
To really grasp the elegance of this, we need to understand the roadblock they were hitting. What was fundamentally flawed with the state-of-the-art smaller models at that time?
Well, we have to look at the cutting-edge, efficient architectures right before this paper. Models like Exception and ResNet.
Yeah, okay.
These models use a clever technique called depth-wise separable convolutions to save compute.
Let's break down what a traditional convolution does first, just as a baseline.
Sure. In a standard convolutional layer, the mathematical filter slides over the image and looks at the spatial dimensions.
The width and height of the pixels.
And it simultaneously looks across all the input channels. So if it's the first layer, those channels are red, green, and blue.
And in deeper layers, those channels represent complex extracted features.
Right. Now, looking at the spatial arrangement and the channel mix at the exact same time requires a massive, dense matrix multiplication.
It is incredibly expensive.
So depth-wise, separable convolutions attempted to break that expensive monolithic operation into two cheaper, distinct steps.
They split the workload.
First, they perform a spatial convolution on each channel, completely independently.
So the filter looking at the red channel only looks at the red channel's spatial layout.
The filter looking at the green channel only looks at the green. This is the depth-wise part.
And that is computationally very lightweight.
Very. But because those channels need to eventually share information, the second step is a dense one-by-one convolution.
Also known as a pointwise convolution?
Exactly. This one-by-one filter doesn't look at the surrounding pixels at all. It just looks at one single pixel location, but it drills down through every single channel simultaneously.
To mix the information together.
Yes.
So they successfully made the spatial part of the math cheaper, but the computational burden was just shifted into that channel mixing phase.
Correct.
How much of a problem was that in practice?
In massive networks running on servers, this trade-off makes a lot of sense. You save overall compute.
But on mobile?
The paper highlights a very specific data point to illustrate the flaw when you shrink these models. In a standard miniature ResNet unit, the authors calculated that these one-by-one pointwise convolutions were eating up an astonishing 93.4% of the total multiplication adds.
93.4%.
Yep.
That means virtually the entirety of the processor's time and battery power is being spent just mixing channels together.
Rather than actually analyzing the spatial features of the image.
Wow. So when you have a strict compute ceiling of, say, 40 megaflops, and 93% of your budget is consumed by these dense one-by-one convolutions,
you are forced into a devastating architectural compromise.
you have to cut corners somewhere.
To keep the total math under your 40 megaflop limit, you have to drastically reduce the number of channels in your network.
And the number of channels dictates the network's width.
Right. And in deep learning, width directly correlates to the network's capacity to learn a diverse vocabulary of features.
If you shrink the width too much, the network simply cannot learn enough distinct patterns to be accurate. Let's use an analogy for the listener to really ground this.
Go for it.
Imagine you're trying to solve a complex puzzle, but because your tools are too heavy, the one-by-one convolutions, you're only allowed to look at 3 puzzle pieces at a time.
Limited channels.
Exactly. You're going to fail. You need more pieces. Or think of it like a digital camera sensor.
Okay, I like that one.
If you have a high-resolution 24-megapixel sensor, you can capture incredibly complex, high-frequency details.
The individual leaves on a tree, the texture of fabric.
That's a wide network with many channels. But if you are forced to use a tiny 1-megapixel sensor, a narrow network, you can't capture that detail.
Feeding a complex image into a 1-megapixel sensor just gives you a blurry, unrecognizable mess.
You don't have the hardware capacity to capture the fundamental shapes. So the authors needed a way to make those one-by-one channel mixing convolutions lighter.
So they could afford to buy back more megapixels, so to speak.
They needed more channels.
And they reasoned that if splitting things up worked well for the spatial layers, why not apply a similar logic to the one-by-one pointwise layers?
Which leads to their first major breakthrough.
Pointwise group convolutions.
Right.
Instead of having every output channel look at every single input channel during the mixing phase, which is that massive 93% matrix multiplication, They divided the channels into distinct, isolated groups.
So let's say you have an input with 64 channels, and you decide to create 4 groups.
Now, a set of convolutional filters only operates on the first 16 channels. Another independent set operates only on the next 16, and so on.
You are erecting strict mathematical walls between these groups of channels.
Yes, each group is doing its own calculations completely blind to what the other groups are doing.
And the mathematical efficiency gained from those walls must be immense.
It is. By dividing the work into a certain number of groups, which we'll call variable g, you effectively cut the computational cost of that layer by a factor of g.
So if you use 4 groups, the compute required for that mixing layer drops to roughly a quarter of what it was.
Exactly. And this is the crucial lever of the entire paper. Because they save so much of their compute budget right here, they could reinvest those savings
into adding more feature map channels overall.
They made the network significantly wider while staying under the 40 megaflop speed limit.
And as we established, a wider network can encode much richer, more complex representations. But here's where it gets really interesting. Those mathematical walls introduce a severe architectural side effect.
By dividing the channels into independent groups to save compute, they created a massive silo effect within the network.
How so?
The authors illustrate this brilliantly in Figure 1A of the paper. They show what happens if you simply stack multiple pointwise group convolution layers on top of each other.
Right, just layer after layer of isolated groups.
The outputs from a certain group are only derived from the inputs of that exact same group.
Yeah.
The information flows straight up the network in parallel, isolated columns.
There's absolutely no crosstalk between the groups.
The feature information is trapped inside its designated silo.
How does that lack of crosstalk affect the network's ability to actually learn and recognize objects?
It severely cripples the core mechanism of deep feature representation.
Because neural networks rely on high-dimensional synthesis.
The entire point of stacking deep layers is to take simple, fundamental features, like a vertical edge or a patch of brown pixels, and combine them into more complex concepts in the next layer.
Like a furry texture.
Exactly. And then the next layer combines those textures to form shapes, like a paw or an ear.
So if group 1 is strictly looking at edges, and group 2 is strictly looking at colors, and they never communicate.
The network can never mathematically synthesize the concept that a specific curved edge and a specific brown color together form a dog's ear.
You are essentially training a series of isolated, very narrow subnetworks rather than one cohesive, powerful model.
Yes. So the authors realized they had to engineer a way to force these isolated silos to share information.
But they had to do it without accidentally reintroducing the massive computational costs of a dense one-by-one convolution.
They needed a communication bridge that cost virtually 0 FLOPs.
Which reveals the paper's elegant solution to the silo problem, the channel shuffle.
The goal is simply to get the groups talking to each other before the next layer begins processing the data.
And the author's solution is incredibly intuitive.
Imagine the output channels from the first group convolution layer. Instead of feeding them directly into the corresponding group in the second layer,
the network takes those output channels, divides them up into subgroups, and then systematically distributes those subgroups evenly across all the different groups in the next layer.
It functions exactly like dealing a deck of cards.
Right. If you have 4 players, you don't just hand the top quarter of the deck to the first player, the next quarter to the second, and so on.
You deal them out one by one, sequentially, so that every player ends up with a completely mixed hand drawn from the entire deck.
That analogy maps perfectly to the mechanics. You are shuffling the deck of feature maps.
And the specific mathematical implementation of this routing is brilliantly simple.
They didn't design some complex algorithmic routing protocol, did they?
No, because that would require processor cycles to figure out where data should go. Suppose you have a convolutional layer divided into G groups, and its output has a total of G times N channels.
Okay.
To shuffle them, you just take that output tensor and reshape its channel dimension into a 2D matrix of shape Gn.
So you make a grid out of it.
Then you perform a standard matrix transpose, swapping the rows and columns so the shape becomes Ng.
I'll bring it on its side.
Finally, you just flatten that matrix back out into a 1D sequence of channels.
That rigid, simple sequence of reshape, transpose, and flatten perfectly and evenly distributes the channels.
The subsequent group convolution layer is now guaranteed to take inputs from every single group of the previous layer.
What's remarkable is that reshaping and transposing matrices doesn't require any floating point arithmetic.
It doesn't use the processor's calculation units at all.
It just involves moving pointers around in the device's memory. It's computationally free.
But there's a deeper requirement for any deep learning architecture that the paper specifically highlights.
Right. For this shuffle to be viable, the operation has to be differentiable.
Let's unpack what that means for the listener, because it's the bedrock of how neural networks learn.
To understand why differentiability is non-negotiable, we have to look at how a network is trained.
During training, you feed an image of a cat into the network, and it makes a prediction.
If the network predicts dog, it has made an error.
The training algorithm, typically stochastic gradient descent, has to figure out how to adjust the millions of internal weights to make the correct prediction next time.
It does this through a process called backpropagation,
which uses calculus, specifically the chain rule, to trace that error backwards through every single layer of the network,
calculating a gradient for each weight that tells it how much it needs to change.
And if you insert a step into your network, that calculus can't flow backward through brick.
The learning process just hits a brick wall.
Exactly. If an operation is non-differentiable, meaning you can't calculate its derivative, the error signal cannot pass through it.
The layers before that operation would never get updated. They would never learn.
But because the channel shuffles reshape, transpose, and flatten operations are just deterministic, fixed spatial rearrangements of data, the calculus is straightforward.
The gradients just flow backward along the exact same shuffled paths.
There are no learned parameters in the shuffle itself.
This means the channel shuffle can be baked right into the architecture as a standard permanent layer.
And the entire network can be trained end to end.
The network actually learns how to extract features with the embedded knowledge that its outputs are going to be systematically shuffled and recombined in the next stage.
It's incredibly elegant.
So we now have these two powerful tools: the massive computational savings of pointwise group convolutions and the zero-cost communication bridge of the channel shuffle.
If the mathematical theory was so sound, how did they actually structure the network to take advantage of it?
The authors combine these operations into a core building block they call the ShuffleNet unit,
which is heavily inspired by the classic residual bottleneck block, an architectural concept made famous by the ResNet models.
A traditional residual block features a main processor path alongside a parallel shortcut path.
This shortcut path simply takes the original input data and bypasses the main processing block entirely, adding itself directly to the final output.
This is crucial for gradient flow in very deep networks.
It prevents the error signal from degrading as it travels backward.
The ShuffleNet unit adopts this overall framework but ruthlessly optimizes the main processing path for mobile constraints.
It initiates the sequence with a one-by-one pointwise group convolution.
This serves as the bottleneck.
It deliberately compresses the number of channels to make the subsequent math cheaper.
And immediately following that compression, it applies the channel shuffle operation to thoroughly mix the grouped information,
getting that crosstalk happening as early as possible in the block.
Yes, ensuring the features are fully integrated before the heavy spatial lifting begins.
Once the channels are shuffled, the unit applies a 3x3 depthwise convolution.
And as we discussed, depthwise means applying a single spatial filter to each channel independently without mixing them.
Finally, the unit utilizes one last one-by-one pointwise group convolution.
This step acts as an expansion layer.
It increases the channel dimensions back out so they perfectly match the dimensions of the shortcut path, allowing the two paths to be seamlessly added together at the end.
There's a highly counterintuitive design choice embedded in this unit that I think reveals a lot about the difference between academic theory and real-world engineering.
The depthwise convolutions.
Yes. The authors utilize depthwise convolutions, which are universally praised as the incredibly cheap, highly efficient way to process spatial data.
Right.
Yet they deliberately restrict these depthwise convolutions only to the bottleneck phase of the unit, where the channel count is at its absolute lowest.
Which seems odd at first glance.
If depthwise convolutions are so wonderfully efficient, why wouldn't you use them everywhere? Why quarantine your most efficient operation to the narrowest part of your network?
This is where the paper brilliantly pivots from abstract whiteboard math to the harsh physical realities of hardware engineering.
Theoretical speed doesn't always equal real-world speed.
In pure mathematical theory, counting raw FLOPs, depthwise convolutions have a spectacularly low computational complexity.
But the authors discovered a painful reality when they actually tried to execute these operations on low-power, mobile silicon.
Depth-wise convolutions are surprisingly, frustratingly slow in practice.
If the mathematical equation is simpler and requires fewer steps, how can it take the processor longer to finish?
It entirely comes down to a metric called the computation-to-memory access ratio.
Okay, let's look at how a mobile system on a chip, or SUFLE, physically operates.
When the processor's arithmetic logic unit, the part that actually crunches the numbers, needs to execute an operation, it cannot just magically access the image data.
It has to send a request across a physical memory bus to fetch the data from the device's RAM.
Pull it into the chip's local cache, perform the math, and then write the result back out to memory.
In dense operations, like standard heavy matrix multiplications, you fetch a large chunk of data once.
And the processor reuses that same data many times for various overlapping calculations.
The memory bus is quiet, and the arithmetic units are kept constantly busy. It's highly efficient.
But depth-wise, convolutions operate differently.
Because they are incredibly fragmented by design.
Because each channel is processed totally independently, the processor has to fetch a new set of weights and a very specific tiny slice of the image for the red channel.
Do a microscopic amount of math and write it back.
Then it has to flush the cache, fetch a completely new set of weights and a new slice of data for the green channel, do a tiny bit of math, and write it back.
The processor's arithmetic units end up sitting idle, twiddling their thumbs.
While the chip spends almost all of its time waiting for tiny fragments of data to crawl across the memory bus.
The operation isn't compute-bound. It is heavily memory bandwidth bound.
So just because you drastically reduce the number of multiplications on paper, it doesn't mean you reduce the latency in the real world.
Especially if your architecture constantly starves the processor for data.
The authors recognized this critical hardware bottleneck.
By intentionally restricting the 3x3 depth-wise convolutions to the narrowest part of the bottleneck, where the spatial feature maps have been compressed to their smallest possible size.
They minimized this memory access overhead as much as physically possible,
while still managing to gain the necessary spatial filtering benefits.
It's a remarkably pragmatic, hardware-aware architectural concession.
They also outline a specific variation of this unit for situations where the network needs to actively reduce the spatial resolution of the image.
A unit utilizing a stride of 2.
Meaning the filter moves 2 pixels at a time instead of 1, effectively halving the image dimensions.
But if the main processing path shrinks the image, but the shortcut path just passes the original larger image through, you can't mathematically add them together at the end.
The matrix dimensions would be mismatched.
To solve that, in the strided version of the unit, they implement 2 precise modifications.
First, they add a 3x3 average pooling layer onto the shortcut path.
Average pooling simply takes a 3x3 grid of pixels and averages their values into a single pixel,
effectively shrinking the spatial dimensions of the shortcut path to perfectly match the main path without adding complex learned parameters.
Second, and quite importantly, instead of adding the main path and the shortcut path together element-wise, where you add pixel value to pixel value, they concatenate them.
Concatenation simply takes the channels from the main path and the channels from the shortcut path and stacks them side by side.
As the paper highlights, concatenating rather than adding makes it incredibly easy to significantly enlarge the total channel dimension of the network.
You are simply bolting more channels onto the tensor, giving the network more representational capacity with virtually zero extra computational cost.
So we have this highly optimized hardware-aware unit. They stack these units together to form the complete ShuffleNet architecture, organized into a series of stages.
Now let's transition to how the authors actually validated this design. The experimental setup isn't just a copy-paste of how you'd train a massive supercomputer model.
They tested this on the ImageNet 2012 classification dataset, which is the gold standard benchmark.
But there are some highly irregular details in their training protocol that stand out. Normally, removing data augmentation is considered a recipe for disastrous overfitting.
Why did the authors intentionally break the standard rules of training for these tiny models?
There are subtle yet fundamental behavioral differences when you train models at the extreme low end of the compute spectrum.
The authors explicitly note 2 major deviations from the standard training configurations used for large models like ResNet.
First, they utilized a significantly lighter weight decay setting.
4E5 instead of the standard 1E4.
Weight decay is a core regularization technique in machine learning. It artificially penalizes the network for developing very large internal weights.
The goal of weight decay is to prevent the network from simply memorizing the exact pixels of the training data, which is overfitting.
Forcing it instead to learn generalizable underlying patterns.
Second, they used far less aggressive scale augmentation during the data pre-processing phase.
Usually, before feeding an image to a network, you warp it, stretch it, dramatically crop it, and alter its colors.
Again, this makes the training task artificially harder, forcing a massive network to learn robust, invariant features.
But you only need to penalize memorization if the network actually has the capacity to memorize in the first place.
And that is the profound insight the authors leveraged regarding constrained architectures.
A 40 megaflop network simply does not possess the capacity, the sheer volume of parameters to memorize the millions of images in the ImageNet dataset.
The primary pathology these tiny networks suffer from is not overfitting. It is underfitting.
They actively struggle to capture even the most basic underlying patterns because their architectural vocabulary is so severely limited.
Therefore, applying heavy regularization techniques like aggressive weight decay or extreme data augmentation actually acts as a hindrance.
It's akin to taking our 1 megapixel camera sensor and deliberately shaking it while taking a photo of a complex scene.
You aren't helping it learn robust features. You are just destroying the faint signal it was barely able to capture.
You have to make the training data slightly cleaner and easier to digest, and you have to allow the network's weights to grow a bit more freely.
To coax the absolute maximum possible learning out of that highly restricted capacity.
So after tweaking the training environment to suit a micromodel, they ran the tests. Let's look at the ablation studies.
This is the part of the paper where they systematically disable or alter specific parts of their architecture to prove that their novel interventions actually cause the performance gains, rather than just getting lucky.
What happens to the accuracy when you change the number of groups denoted by the variable g?
Table 2 in the paper provides a definitive breakdown of this behavior. The authors constructed several ShuffleNet models of identical overall computational complexity, but they varied the number of groups in the pointwise convolutions.
They started with G1.
Which effectively means there is no grouping at all. It's just a standard, dense 1-by-1 convolution, making the architecture behave very similarly to an exception network.
They then scaled the groups up to G2, G4, and G8.
The empirical results are clear-cut. The models utilizing group convolutions, where G is greater than 1, consistently and significantly outperform the baseline model without groups.
And the mechanism behind that performance boost is exactly what they hypothesized. Dividing the compute into groups freed up the budget,
which allowed them to build a wider network with more channels.
Yes. But what is particularly revealing is the scaling behavior they uncovered.
The smaller the overall scale of the network, the more disproportionately it benefited from having a larger number of groups.
For example, on their baseline 1x scale model, increasing the groups from 1 to 8 provided a respectable 1.2% boost in accuracy.
However, for their ultra-tiny 0.25x scale model, making that same jump to 8 groups provided a massive 4.4% accuracy boost.
This data strongly corroborates their core thesis. Tiny, heavily constrained networks are desperately starved for channels.
By deploying aggressive grouping, you liberate compute cycles to widen those feature maps.
For a tiny network, that extra width is the absolute lifeline that preserves its ability to recognize objects.
But logic dictates there must be a ceiling to this trick. You can't just set the number of groups to 1,000 and expect infinite accuracy, right?
You cannot, and the authors are transparent about the architectural limits of this approach.
Table 2 clearly shows that if you take a highly constrained model, like the 0.5x scale version, and push the group number too high, say G equals 8, the classification accuracy actually begins to degrade.
The reason for this degradation relates back to the filters themselves.
As you increase the number of groups while strictly maintaining the overall computational limit, the number of input channels that each individual convolutional filter is permitted to look at becomes dangerously thin.
If a filter in a group is only receiving data from 1 or 2 channels, it simply lacks the foundational context required to generate a mathematically meaningful feature.
The network's representational capability collapses under the extreme siloing, even with the channel shuffle trying to mitigate it.
You have to meticulously find the architectural sweet spot, balancing the overall width of the network against the depth of the individual filters within each group.
Having proved that their internal mechanics function as designed, the authors set up the ultimate industry showdown:
At the time this paper was published, Google's MobileNet was essentially the reigning heavyweight champion of small, efficient mobile models.
When they put ShuffleNet head-to-head against MobileNet under the exact same constraints, what was the outcome?
This comparison is where ShuffleNet firmly established its legacy. The authors direct our attention to Table 5, which contrasts classification scores across various strict complexity tiers.
Under the punishingly low budget of 40 megaflops, ShuffleNet achieved an absolute top 1 error rate that was a full 7.8% lower than MobileNet's error rate.
A 7.8% reduction in error on a benchmark as rigorous as ImageNet is not a minor incremental tweak.
In the realm of computer vision, that represents a generational leap in performance at that specific compute tier.
It is a massive margin of victory. MobileNet was a highly optimized, brilliantly engineered architecture.
But its foundational reliance on dense one-by-one pointwise convolutions fundamentally hard-capped how wide it could be built at the 40 megaflop level.
ShuffleNet's architecture simply bypassed that mathematical bottleneck entirely.
Furthermore, the authors didn't just compare it to contemporary mobile models. They compared it to legacy benchmarks to show how far the field had come.
The ShuffleNet 0.5x model managed to achieve the exact same level of accuracy as the classic AlexNet,
the monumental model that originally shattered the ImageNet benchmark back in 2012.
But ShuffleNet achieved that 2012 supercomputer-level accuracy with a theoretical complexity that was 18 times lower.
They packaged a historical breakthrough into a fraction of a modern smartwatch's power budget.
They also conducted tests swapping out the internal structures, didn't they?
They did. What happens if you take the ShuffleNet macro architecture, but replace the specialized ShuffleNet units with standard layers from other famous models?
They detailed this in Table 4. They built networks using the same overall compute budget, but swapped the core units for VGG-like layers or standard ResNet bottleneck layers.
In every configuration, the ShuffleNet unit outperformed them.
The authors extract a very clear empirical rule from these tests. Under a strict, unyielding computation budget, the architecture that is designed to allow for the most feature map channels, the widest possible network, will almost always achieve higher accuracy.
For instance, at a 38 megaslot budget, a ResNet-like structural setup could only afford to generate 192 channels in its final processing stage before hitting the compute ceiling.
ShuffleNet, using its groups and shuffles, could afford to generate 576 channels at that exact same compute cost.
That massive surplus of width is the primary mathematical driver of its superior performance.
The theoretical math is indisputably brilliant. The ImageNet benchmark scores are stellar, but the title of the paper specifically includes the phrase for mobile devices.
So we have to ask the critical question. Does an 18x reduction in theoretical math actually translate into a real-world physical speedup when you deploy the model onto actual silicon?
This section of the paper provides perhaps the most sobering and universally valuable lesson for anyone working in edge AI deployment.
The authors did not just stop at reporting theoretical FLOPs on a whiteboard. They rigorously tested the actual physical inference latency on an off-the-shelf ARM-based mobile processor.
Specifically, they targeted a single core of a Qualcomm Snapdragon 820.
The very common flagship tier mobile chip from that era.
Let's examine the data in Table 8. You'll recall that the ShuffleNet 0.5x model possessed a theoretical 18x complexity reduction compared to AlexNet.
Right. The math required was reduced by a factor of 18.
However, when they actually compiled the model and ran it on the physical Snapdragon silicon, the execution time did not decrease by a factor of 18.
It achieved roughly a 13x actual speedup in milliseconds.
A 13x speedup is still an incredible engineering achievement, but it reveals a significant gap between the theoretical projection and the physical reality.
Where did that extra execution time go? What was the processor doing if it wasn't doing math?
The lost time is almost entirely attributable to the very hardware bottlenecks we discussed regarding depth-wise convolutions.
Memory access overhead and the inherent inefficiency of executing highly fragmented operations on a mobile bus architecture.
The authors derived a painfully empirical rule of thumb from these hardware deployments. In practice, every 4x reduction you achieve in theoretical mathematical complexity only translates to roughly a 2.6x actual speedup on the physical mobile hardware.
That is a staggering inefficiency. You're losing nearly half of your theoretical performance gains simply to the physical friction of moving data from the RAM to the cache and back again.
It highlights a massive blind spot in purely mathematical AI research. And the paper provides a perfect, almost painful case study of this disconnect through their attempt to integrate squeeze and excitation, or SE blocks.
SE networks were a concurrent, highly celebrated breakthrough in the field.
They essentially bolted a lightweight attention mechanism onto existing networks.
An SE block looks at the entire spatial feature map, uses a global average pooling operation to squeeze all that spatial information down into a tiny vector.
Uses a tiny, fully connected layer to analyze it.
And then expands it back out to individually reweight the importance of each channel.
On paper, it boosts accuracy significantly with an almost negligible increase in theoretical FLOPs.
Naturally, the ShuffleNet authors bolted these SE modules onto their architecture.
And initially, the theoretical results matched the hype. The accuracy jumped significantly.
The error rate dropped down to a highly competitive 24.7%.
And just as promised, the theoretical FLOP count barely twitched.
Sounds like the holy grail. Increased accuracy for zero computational cost.
It is a free lunch on a whiteboard. But when they actually deployed that SE-enhanced ShuffleNet onto the physical mobile device, the execution latency skyrocketed.
It ran 25% to 40% slower than the base model.
40% slower, even though the actual number of mathematical operations barely increased?
Because the physical nature of the SE module's math is exceptionally hostile to mobile hardware.
That global average pooling operation forces the mobile processor to scan and read the entirety of the spatial feature map across every single channel, just to compute a tiny handful of numbers.
Which it then has to write back across the entire tensor.
It requires massive sweeping memory reads and writes with very little actual arithmetic taking place in between.
It absolutely saturated the memory bandwidth of the Snapdragon chip.
This specific failure perfectly underscores the paper's central, enduring lesson regarding edge computing.
FLOPs are a woefully incomplete metric.
If your neural architecture is hostile to the physical silicon realities of memory access patterns and cache structures, your theoretical mathematical efficiency is entirely meaningless in the real world.
That is a phenomenal insight that still plagues AI deployment today.
Before we move to our final segment, we should note that the authors also verified this architecture wasn't just highly tuned to cheat the ImageNet classification benchmark.
They took the ShuffleNet architecture and deployed it as the backbone for MSCOCO object detection.
Object detection is a vastly more complex spatial task than simple classification.
The network doesn't just have to say there is a car in this image.
It has to mathematically draw a precise bounding box around the exact pixels of the car, the pedestrians, and the traffic lights, all simultaneously.
Table 7 demonstrates that ShuffleNet generalized beautifully to this complex task, significantly outperforming MobileNet's detection scores as well.
Proving that the wide shuffled feature representations it learned were robust and highly adaptable.
The object detection results cemented ShuffleNet not merely as a clever mathematical trick for one specific dataset, but as a foundational, highly generalizable architectural paradigm for any visual task operating under severe hardware constraints.
We are now entering the novel notions segment.
Always my favorite part.
Please note, the ideas discussed in this final segment are for entertainment purposes only. We are taking the core legacy of the paper and stretching it to extreme, highly speculative limits to see what concepts emerge.
Let's hear it.
So, here is a scenario-based thought experiment. The entire genius of the ShuffleNet paper rests on using the mathematical operations of reshaping, transposing, and flattening to allow highly siloed, compute-starved groups to cross-pollinate information efficiently without a massive, dense calculation.
Right.
What if we took that concept out of the microscopic traces of a single piece of silicon and applied that exact mathematical routing to physical, decentralized hardware?
That is a fascinating premise. Let's explore how the mechanics of a channel shuffle would map onto physical space.
Imagine a swarm net, a literal swarm of hundreds of autonomous microdrones, perhaps the size of large insects.
Deployed across a forest for environmental monitoring or a collapsed building for search and rescue.
Because they are so physically small, their onboard batteries can only support the most rudimentary, lowest power microprocessors available.
No single drone in the swarm possesses anywhere near the compute power required to run a full vision model to recognize a complex target, like a survivor's face or a specific chemical signature.
If we map the ShuffleNet architecture onto this physical swarm, each individual drone acts as a single group within a massive decentralized group convolution.
Drone A is programmed to only process the red channel of the visual spectrum.
Drone B is only running algorithms to detect high-frequency vertical edges.
Drone C is strictly processing motion vectors.
They are operating in total computational silos, completely blind to the bigger picture, in order to conserve their microscopic battery reserves.
But for the swarm to actually act intelligently and recognize a complex target, they have to combine those features.
Normally, the paradigm would be that all the drones beam their isolated data back to a massive central server, which acts like the dense one-by-one convolution to mix the channels and make a decision.
But transmitting continuous video or heavy tensor data over Wi-Fi or radio frequencies requires an enormous amount of power.
The sustained radio transmission would drain their batteries far faster than the onboard computation ever could.
The central server model fails at this scale. So instead of relying on a central server, the swarm executes a physical, real-world channel shuffle.
Periodically, the drones physically converge into tight formations.
Crucially, they do not attempt to transmit all their raw data to everyone.
Instead, they execute the mathematical transpose operation physically.
Using highly localized, incredibly low-power optical bursts, like microscopic, high-speed flashes of infrared light, they perfectly swap specific, predetermined subsets of their highly compressed feature vectors only with their immediate physical neighbors in the formation.
So Drone A, which only has red channel data, flashes a tiny compressed piece of that data to Drone B, and in the exact same moment receives a tiny packet of vertical edge data from Drone B in return.
Exactly. Just as Figure 1 SAC in the paper demonstrates reshaping and flattening mathematical channels inside a memory bus, the physical swarm dynamically resorts which drone possesses which specific feature vector for the next layer of inference.
After a split-second optical shuffle, Drone A no longer just has red data. It now holds a mixed tensor containing color, edge, and motion data.
It then breaks formation, performs the next computationally cheap processing step on that newly mixed data, and the cycle repeats.
You are essentially running a massive, distributed physical shuffle net in the sky.
The physical swarm itself is the neural network, utilizing physical proximity and spatial rearrangement to entirely bypass the catastrophic energy cost of dense radio communication.
That is a wild visual, but logically it maps perfectly to the exact routing mechanism the authors designed for their internal memory tensors. It is simply about routing critical information efficiently when energy is your absolute strictest constraint.
It's a brilliant extension of the principle.
Well, that brings us to the end of our analysis. We spend so much of our time in the tech world marveling at the massive billion-parameter models in the cloud.
The ones that require warehouse-sized supercomputers and dedicated power plants just to generate a sentence.
But ShuffleNet forces us to look in the opposite direction and ask a different, perhaps more profound question. As hardware inevitably gets smaller, as microscopic sensors are embedded into every object around us, and as data generation moves closer and closer to the absolute edge of the network, is the true future of artificial intelligence actually going to be defined not by how much massive compute power you can hoard, but by how elegantly and brilliantly you can shuffle the little compute you've got?
That's the real question.
The link to the paper is in the bio in the description. Thank you for listening to this deep dive.